find the derivative of y cubed minus 2y equals x cubed plus 5 with respect to x. Okay, so if we were even going to attempt to do this using what we already know, we would have to try and figure out how to get y on the left hand side and some function of x on the right hand side. Yeah, good luck trying to do that. I assure you it's possible, but it will be a mess, and I mean a right royal mess. A better way is what we call implicit differentiation, and we can take advantage of the chain rule that we just used. We have to remember that y varies with respect to x, so y is a function of x. So what we can say is that the derivative of y cubed minus 2y with respect to x is equal to the derivative of x cubed plus 5 with respect to x. Now let's take the right hand side first because it's really easy. We can split this into two because the sum of the derivatives is equal to the derivative of the sums. So the left hand side is going to be equal to the derivative of x cubed with respect to x plus the derivative of 5 with respect to x. And we know that the derivative of a constant with respect to a variable is just 0 because constants don't change. That's why they're called constants. So this is just plus 0, and anything plus 0 is itself. So this is just d of x cubed by dx, which is just going to be 3x to the power 2. So that's equal to 3x to the power 2. So that's our left hand side. Now our right hand side is again going to break down to d of y cubed by dx minus d of 2y by dx. Now we remember our chain rule. We can say d of y cubed by dx is equal to d of y cubed with respect to y multiplied by dy by dx. And you can see visually how that works, because if you imagine they're fractions, even though they're not fractions, but you imagine they're fractions, these cancel out and you just get dy cubed by dx. So we can do the dy cubed by dx nice and easily. I'm going to do it over here if I can find what happened to my cursor. Dy cubed by dx is equal to, so that's 3y squared, which is dy cubed by dy, and then we've got to multiply that by dy by dx. Okay, so that's our first bit, and then our second bit is d 2y by dx, by the same reasoning, is just going to be 2 times dy by dx. So all of this is equal to 3y squared dy by dx minus 2 dy by dx. And of course all of that is equal to 3x squared. Alright, so now what we have to do is do a bit of algebraic manipulation to get dy by dx on its own, so that's fairly straightforward. We can factor out the dy by dx. Into 3y squared minus 2, and that's equal to 3x squared. And then divide by the 3y squared over 2, and we have dy by dx is equal to 3x squared over 3y squared minus 2. And that is our final answer. So we can get the derivative even when it's not an easy looking function using this very powerful tool called implicit differentiation. Okay, if we'd have tried to do that explicitly, we would have had just the most unbelievable of messes. In fact, let me just quickly show you something. Okay, so if we had tried to solve for y, just look at the mess we would have had to have tried to deal with. Yeah, I wouldn't want to even handle that. So implicit differentiation really helped. And thanks to implicit differentiation, we got the answer in a way that was really straightforward. So implicit differentiation can take something that looks really complicated and actually make it fairly straightforward. It's a extremely powerful tool. Okay, I'll leave you with a question as usual, and I think that just might wrap us up with regard to differential calculus. There is more to differential calculus, believe me, an awful lot more, but I think we've got enough now to be going on with. So I think in the next lesson we'll probably think about moving on to integral calculus. Okay, I hope you enjoyed that, and I'm going to leave you with a question, and I'll look forward to seeing you in the next lesson.